Okay, a slant asymptote is another version of n behavior. In other words, what the graph of a rational function will tend towards as x gets really large. So the way we find slant asymptotes, and really we can do this to find horizontal asymptotes as well, because it's the same concept of n behavior, is to actually divide the polynomials. The rules I showed you for horizontal asymptotes are just faster, but you could also get there with this rule. But the other rules are a shortcut for, oh sorry, didn't mean to hit that, a shortcut for horizontal asymptotes. But for slant asymptotes, we have an n behavior. What I mean by a slant asymptote is it's still a line, just like horizontal, except it's got a non-zero slope. So it's some line that's not horizontal. You could still have a vertical. So you might have a graph that looks something like this. This is an example of a rational function with a slant asymptote. You cannot have a slant asymptote and a horizontal asymptote on the same graph. Let me put one in here to show you that. And why you cannot have the two. Let me see here. Can I undo? Okay. So if it's got a slant, and then let's say it's got also a horizontal, and I put it in red to show you that it's wrong. I cannot have both because they both mean n behavior, meaning as x gets really large, the function tends to it. So either the function as x gets really large, I'm just starting to draw it over here because I don't know what this function would do in the middle, and I don't care. The red line would be n behavior, the red asymptote. It either approaches that asymptote as x gets really large, or it approaches that one, but it can't approach both, and they both have the same meaning. They're saying this is the line you approach. So you can't have both a horizontal and a slant because it's confusing. Which asymptote does it approach? So I like to look at it like that. Let me just do undo here to get rid of this. Okay, so a slant asymptote is just like a horizontal asymptote, but it's just not a horizontal line. It's a line with a slope of something other than 0. They're going to make me undo every dash. Interesting. Okay, so another way that this graph could have been drawn is maybe it goes like this. Okay, those are some rational function possibilities with slant asymptotes. How do you find them? Divide the polynomials. So for example, the only situation where we did not have a horizontal asymptote, if you recall, is when the degree of the numerator was larger than the degree of the denominator. So when that's the case, you may have a slant asymptote. Think about this. If you take a degree 2 polynomial and divide by a degree 1, as in this case, your quotient would be a degree 1 polynomial. If I had a degree 5 and divided by a degree 3, my quotient would be a degree 2 polynomial. And so in both these cases, these quotients will, if you were to graph those functions using a dotted line, those would represent the n behavior. So we don't typically graph anything than the higher of degree 1 for n behavior. In other words, like if I had a degree 5, a rational function where the numerator was degree 5 and the denominator was degree 3, I might have n behavior that follows or approaches this curve. Okay? But we're not going to draw that on there. It starts to get confusing with the graph. We only draw n behavior graphs with asymptotes, with lines. We don't draw asymptotic behavior that's quadratic or even cubic. It'll start to get confusing, okay? So the point is that you can only have a slant asymptote when the degree of the numerator is exactly one higher than the degree of the denominator. So how do we find and graph that asymptote? We do the division. Let's do it here. So for this one, I'll do long division. You could do synthetic, but I'll do long division. So it's going to be 4x times x is 4x squared plus 8x. I then subtract that polynomial, so I get negative 5x. So then I'm going to multiply by negative 5. Oh, sorry, I need to drop down the negative 1. Multiply by negative 5 to get negative 5x minus 10. I then subtract that polynomial to get 9 for my remainder. So remember, one way to write division, if I do this quickly on the side, so what this would mean, one way to write my quotient would be that 17 divided by 3, the rational number 17 over 3, could be written as the quotient plus the remainder divided by the divisor. And that's what we're going to use in this instance. This is how we're going to rewrite this thing. We're going to rewrite r of x as the quotient plus the remainder over the divisor. Okay? And this function will approach, you just use the quotient for your slant asymptote. This rational function will approach this guy right here, this line. So when graphing this rational function, which will be coming up next, you would start by graphing asymptotes typically, or x-intercepts. So if we had to graph a slant asymptote, we would have to graph that line. So I'd go down 5, and then my slope is 4 over 1. So I'd go up 4 and right 1. Up 4, right 1. Okay, down 4, left 1. And then I draw that asymptotic behavior on the graph. That's the asymptote. I don't know what the function looks like, but I've got my slant asymptote on there. Okay, and then from there we could draw the rest of the information for the graph: the x-intercepts, the y-intercepts, the vertical asymptotes, all kinds of stuff. Keep in mind that we don't worry about the remainder. This is okay to have this little extra piece on here, because if I gave you a look at this and said, well, let's pretend I knew what this thing looked like. Let's just say for a second it's this. It has that vertical asymptote, and the graph does this in this little part here. The function value on the graph for large values of x, say even 5, if I plug in 5, my y value is not going to be right on this line. It's going to be slightly above it. That's what this is doing. This is adding a little extra amount onto my y value. So it's almost here. That's why I know the quotient is 4x. The slant asymptote is the quotient 4x minus 5. Because if I were to plug in, say, 5, I would get 15, which that would put me right on the asymptote. But then I'm adding this little bit extra here to get a little bit above it. And the further out I go, the bigger the x I plug in, the smaller and smaller this little amount becomes, because I'm making the denominator smaller. So I'm getting closer and closer to the asymptote, and that's why it's end behavior. So I'm just saying, don't worry that you have this remainder. When you need to find the slant asymptote, you do the division, and the slant asymptote is the quotient. You will get a remainder that is not 0. That's okay in this situation.